There we go. All right. So on Tuesday, we talked about congruent modulo math, which is essentially just saying, okay, before we compare, let's mod everything first. That's basically what it is. Okay. Before we compare, we'll mod it with whatever the base is. So that actually is the basis to understand how we can represent negative numbers in base two. Because if you think about base two numbers, it just doesn't make sense that we can represent something that is negative. But once we understand that, we have modulo, congruent modulo, the that whole concept, then we go like, oh, okay, so we can use that as a mathematical basis to represent negative values, but only using base two digits. So we are not even introducing the usual arithmetic negation symbol in order to say, oh, this is -5. We just say, okay, one of these binary bit pattern is going to represent negative values. Okay, or it has the option to represent negative values. So if you revisit the number wheel, you can see that half of the slots on this wheel, they can represent something that's positive, like 12 in this case, but also a value that is negative, like -4. And I answered the question also that some people probably have in their mind, which is, so which one is it? Okay, if I look at the bit pattern of 100, is it 10 or is it -6? And my answer was, well, why do you care? Well, because that really is the question. Okay, why do you care? What is 1010 representing in your program? It is entirely possible that 1010 is not even considered a number. Okay, it may be corresponding to the intensity of pixels on the screen. It may be indicating back in the dot matrix printer, days. It might just be indicating whether you a pin from the dot matrix print head is supposed to strike the paper or not. Okay, so that means 1010 has no intrinsic meaning. The only time when you really have to know whether 1010 should be interpreted as 10 as a value or interpreted as -6 as a value is when you compare. It does not even matter when you add or subtract. It is only when you need to add, it's only when you need to compare that to another value. Because if you're comparing, then you can say, oh, 1010, if it is 10, it is greater than, say, 00110. Okay, so in the unsigned interpretation, 1010 is greater than 0110 as an unsigned interpretation. But if you choose the signed interpretation, which is using the -6 here, then 1010 is not greater than 0110 because these 8-bit patterns do not have a negative value associated with them. Yes. Mm, the number wheel is more like, what can you possibly interpret a bit pattern as, given a particular bit pattern. So I think it's more useful in that sense. Basically you're given a particular bit pattern, 4 bits in this case. If you need to know what value it is representing, then the number wheel can help you with that. Yes. hmm Because that's how modulo math works. Because because whether you're adding 10 or -6 in modulo congruent 16 math, they are the same thing. Okay, so I'll address that with an actual example. So that's a very good question. There was another hand up front a little bit earlier. Okay, maybe not. Go ahead. hmm just so happens that the most significant bit can also be used to indicate whether the number uh, is non positive or non is negative or non-negative. It just so happens, that the way we choose to do it this way is also, the sign bit also has that property. Yes, that is correct. They can be interpreted as negative. So that was actually more or less a coincidence. Okay, so I'll explain, how the sign, versus unsigned thing works and how to convert the sign. How do you arithmetically negate a number and get the value, after you negate it. Okay, so those are all extremely good questions. So, so the first thing I'm going to do is to address the question of why would, addition and subtraction not care about what a particular bit pattern is supposed to be representing. Okay, so we'll address that first. So we can address that by using an example, okay, which is not very theoretical, but it is probably an easier way to look into it. So we're going to look into something that looks really awful, something along the line of, 1100 plus 1110. Okay, so in base 2. Okay, so everything from here on is kind of in base 2. So we perform the addition. So now this is also a good chance for you guys to practice, how to compute the individual bits when you are adding two binary numbers, but only using logical operations and not so much using the traditional sense of arithmetic operations. So this is Q, this is K, and this is S. Okay. So Q is the exclusive OR between the X and Y. So we have a 0 here, a 1 here, a 0 here, and a 0 here. And then K, because we don't have any previous, addition, so K0 is a 0. So now we have, this also being a 0. This is also going to be a 0. This is going to be a 1. This is going to be a 1. And then S is the exclusive OR between the Q and the K. So that means this is a 0. This is a 1. This is a 0. This is a 1 again. So I just performed, all the logical operations kind of really quickly in my head. Um, but I think after the lab on Tuesday, you guys should know how to do that already as well. Now, can you do it as quickly as I can? I think you can, okay, but do you know why, or where that comes from? I hope after that lab on Tuesday, you guys go like, oh, okay, so we are converting all the relationship between the digits into a circuit, okay, and you can actually see the circuit work, on in the lab of Tuesday. So talking about that lab, do we have any questions about the lab on Tuesday? Yes. Okay, so yep, I can surely do that. So this is just a digression from this little topic here, but it's okay. So let me. Oh, okay, that won't work. Yes, I believe so. Let me double check. Yep, I am recording. It's recording. Okay, so in addition to am I recording, there are two additional questions to ask. Am I recording the right screen? Because if I'm recording the wrong screen, you just don't see anything moving. And also, is the voice included in the recording? Because it happened in the past that I used the wrong audio channel, so the whole thing was a silent movie, which is entertaining on its own. Okay, but there are a lot of time when there's nothing going on because I'm just verbally explaining. Yes, say say again. If what happens? Oh, or we can crowdsource. You guys can all do the recording on your own, and then we just we'll have a super what? Oh, I can just give you the consent. Okay, so most professors, would not by default let you guys record a class. That's my understanding, because I have asked, people about it. But in my class, since I'm recording it anyway, so, I don't see why I cannot let you guys also do some recording on your own. Anyway, so this is where you can find all the gates. I mean, it is kind of spelled out here, as gates. So, that's where you can do it. We'll be doing okay so far. Okay. And also the gates are, named as well. Okay, so and, or, and then finally the not gate. I mean, those are the only three that you need. Plus the exclusive or, which is XOR. But my notes also spelled out XOR as well. I made sure that I updated my notes before the lab. All right. So is that okay? So that addresses that particular issue. Okay, cool. All right, so now we look at this and go like, okay, so let's interpret X and Y, both signed and unsigned, and see if the sum makes sense or not. So with X, if it is unsigned, okay, so I'm gonna erase this part here just because it's not useful. So I'm gonna use U for unsigned and then use S for signed. So unsigned X is a 12 in base 10. And then 1110 is 14 in base 10. 1010 is 10 in base 10. But we have an overall carry of 1, which is a 16. 10 plus 16 is 26, which is also what you normally would get when you add 12 to 14. Is that okay? So is everybody convinced that in the unsigned interpretation, the addition makes sense? Okay, so let's check out the signed interpretation. So in the signed interpretation, this is -4, this is -2, and then 1010 is -6 by itself. Okay, so yeah, it makes sense again. So I don't have any problem with, you know, performing addition here, not needing to know whether the bit patterns are signed versus unsigned. So does that help address your question? Go ahead. Yep. So we'll check that out too. Okay. So let me use a different page, and this time we have 1101 plus 0110. Okay. Let me see. Would that overflow? Yep, that's going to overflow. Let's not do that. Let's do this. Okay. All right. So now we perform the addition. Once again, we have x, y, q, k, t. Oh, some s right here. This is exclusive OR, so one exclusive OR with 0 is a 1, 0, 0 is a 0, 1, 1 is a 0, 1, 0 is a 1, and then this is a 0 to begin with. That's a 0, that's a 0, that's a 1, and that's a 1 as well. And then 1, 0, exclusive OR is a 1, 0, 0, 0. Okay, all right. So now we look at this and go like, okay, does that make sense? So now, once again, we have the signed versus the unsigned interpretation. So this is the unsigned interpretation. This is the signed interpretation. 1101 unsigned is 13. This is a 4. And this is a 1. But since it has an overall carry of 1, which is a 16, so now it is actually representing a quantity of 17. Um, well, 13 plus 4 is 17. Seems to work out. So now we look at the signed interpretation. In the signed interpretation, this is -3, this is still 4, and this one is 1. Well, I don't think we can argue that -3 plus 4 is 1. So it works out too. All right. The reason why it works out is because, okay, so do we remember what is congruent modulo in this case, 16? So now we take a look at that thing. Okay, 13 is congruent modulo 16, and that's my notation to mean that it is congruent modulo. So we know this is true, okay, because we that's how we worked out the number wheel. But what does it mean when we say congruent modulo 16? It means 13 can be expressed as some v plus some ka times 16. Negative 3 can be expressed as the same v plus kb times 16. V itself has to be greater than or equal to 0, but it has to be less than the base, okay, which in this case is 16. And then Ka, Kb must be integer. So I'm going to use the um, math notation here. So now the question is that true? Okay, well, if we make V exactly 13, then Ka is a 0. If V is 13 and I choose KB to be negative 1, this equality works out as well. So that means both of them are really just V plus some integer times 16. The same thing can be done with 4. Okay, so 4 has another constant. So when we add those two, the v's, okay, of those two will kind of add up. The other side is not a problem because we are still looking at some constant times 16 and then plus some other constant times 16. It is still just an integer, okay? Ka plus kb is just an integer, or kc and kd in the case of the other number. It is still an integer. So that's why it works out in both cases. So that's kind of the mathematical basis of why we choose to represent negative values using basically in this case using KB being negative 1. Yes, yes. hmm But not so much in the sign interpretation does not take a look at the overall carry. Yep. Only in the unsigned interpretation that is correct. Yep. hmm So are we good so far? Okay. Um, most other classes won't tell you anything behind why it works. Okay, they won't explain why it works. They will just give you a formula, okay, and say, okay, just memorize this and you're good. But I want to look into the actual math behind the scene and understand why it works. So that's really just the way that I works. That's the way I understand things, and that's the way I operate. Okay, if I need to solve a problem, I need to know everything there is about the problem that I'm solving. All right. So are we good so far? Do we have any additional questions about addition and subtraction and why it doesn't matter whether we choose the signed versus the unsigned interpretation, addition and also subtraction works too. And if you want to practice, you can also practice with subtraction. You will find that most of the time it works out until you're out of range. So because in sign interpretation, you can end up with a result that is out of range, and then the sign doesn't make sense anymore. But we'll talk about that when we talk about comparison of integers. Yes. Well, unsigned gives you twice the range of values. That is That is correct. So in some cases, if you do, okay, let's take the case of a 16-bit integer. Okay, so with 16 bits, if you go for unsigned, the largest value it can represent is 65,535. If you use signed interpretation, then the largest value is only 32,000. I cannot remember. 30, 32,000 something. Okay, so you only get half the range because you have to reserve the other half of the bit combinations for the negative values. So, it's just an optimization kind of thing, so that, if you don't need to use more bits to represent something, you don't use more bits to represent something. In real world, so that's not even an integer anymore. So we are not even going to be that's not even. Yes, that is a double, which is, and the full name of a double in C and C++ is the IEEE double precision floating point number. And we will talk about that, just not now. Yeah, so in those cases, you have no choice but to use the signed representation. But when you're trying to use a variable to track the indexing through an array, there's no reason why you should use a signed integer in that case. Now, does are you really gaining a whole lot by using signed, unsigned versus signed? The answer is no, not a whole lot. Yeah, but nonetheless, you still have a choice. I mean, the programming language is just giving you a choice. How you want to use the types is up to you. Does that make sense? Okay. All right. Okay. So now that we understand how negative values are represented, then the next question is, what about arithmetic negation? Okay, so I hope you guys have had a chance to read the notes before the class, and I'm just going to re-emphasize and just nag people again, about the importance of reading the notes. So we are pretty much done in before this section here. So now we are moving into arithmetic negation in base 2. The following is true regardless of n. Okay, so let's take a look at this thing here. So n is the base, okay, not so much the base, but it is what we are modding the numbers to. So negative v is congruent modulo n with negative v plus k times n. I think that kind of goes without saying for some integer k, obviously. Does that make sense? It is by definition, okay? It is by definition that negative e is congruent modulo n with a value that is the same as negative e, but you just add a multiple of n to it. In other words, if you think about that wheel, okay, negative v is pointing the needle at some place, okay? I have to be very careful with my hand gesture, thanks to Elon Musk. Yes, let's point here. Okay. Now there's no confusion. Okay. So let's yeah. So I'll just point here. There's no way, and I extend my hand like this. Okay. There's no way it can be confused. So so let's just say that negative v is pointing to this position, okay, as a negative value. And from your perspective, it really is on this side, right? Because you can see that on the number wheel, the negative values are always on the um, on your left hand side. Okay. So every time we add n to it, it just goes one full revolution back to the same place. Okay. If you want to turn the hand exactly k full revolutions, it still end up at the same place. Basically, anything that ends up at the same place, they are considered to be congruent modulo n. N is simply the number of slots on that wheel. So is that helping to kind of give you guys a visual of how congruent modulo math works? Okay, we only get so many slots on that wheel. Okay, and we're just asking, okay, how many times do I have to turn the hand to get to the value that I want? But it is a wheel, so if the wheel has n slots and you're turning n slots, you're still ending at exactly the same place. Is that okay? Yep. Okay. All right. Good. Any questions about that analogy? Okay, so with that, okay, now we look at this math here. Okay, it is a little bit long, so I'm going to explain it, kind of step by step. So we have just established that negative v is congruent modulo n with negative v times some k, which is an integer, times n. And I don't think anyone is going to argue that 1 is an integer. Is that okay? Okay, so over here, you can just kind of imagine that there's a 1 times n here, and so k equals to 1. Okay, so now we have a single equal. This is not a typo. I'm switching from congruent modulo n to just equality here because it really is equality. What did I do? I pull the 1 away from here and then add the 1 again over here. Is that okay? So most of you use algebra to simplify something. I can use algebra to make things more complicated than it seemingly needs to be. Okay, but there's a reason why I do this. Okay, so now we also say that this whole thing here, negative v plus n minus 1, the whole thing plus 1, the entire thing, equals to this whole thing, plus 1. So what I did is just simple algebra by moving things around a little bit. So I'll be okay with the equality here. I'm talking about this particular equality. And with all the hand gesture controversy, it's probably be safer for me to use the mouse pointer. It's like I don't want people to take a picture of me kind of somewhere in the middle of a motion and go like, "Oh, Tech just did a salute." It's like, really? Okay. So right here, are we good with that equality? Are we okay with the algebra that is involved to make that equality works? We good? Okay. All right. So you go like, so what have we done? Okay, we haven't done anything useful. Okay, this is algebra in as in anyone who has taken algebra 2 could have done this too. So now we go like, but we have just established that negative v is congruent modulo and with this mess over here. And you go like, I don't see how this is helpful. Okay, well, the thing is, we know something about n. This n here is not just any non-negative integers. Okay, this n here is always a power of 2. Let me say that one more time. It is always a power of 2 because when you only have 4 bits, what is that n? How many slots is in the wheel, or how many unique bit combination do we have when there are only 4 bits? Close. Yes, 16. Very good. So you're very good. Okay, so you said 15 and you look at my facial expression and go 16. That is good. Okay. So if I use W, okay, so let me go back to this W here. If W is 8, what are we talking about? What is N? 2 to the power of 8 is 256. Okay, I'm actually kind of shocked that people do not have that memorized. I think I got at least memorized up to 10, 11, 12, 13, 14, at least 14. Because if you're in computer science, this is important. 2 to the power of an integer. You really should be familiar with those particular values. Okay, so so you guys go like, okay, fine. What is the big deal? Okay, what is the big deal that n is 2 to the power of some non-negative integer w? Okay, so that's the next question. So the notes here said, okay, so I'm just substituting wherever n was, I just replace it with 2 to the power of w. Okay, that's easy peasy because all I'm saying is n equals to 2 to the power of w. So what exactly is the big deal? So now you look at this example here. So let's just say that w is 4, okay, which is what the number wheel is about. W equals to 4 and v equals to 3. Then negative 3, because you remember v is 3, so negative v is negative 3. So negative 3 is congruent modulo 16 with 16 minus 1, the whole thing, minus 3, the whole thing, plus 1. Okay. In other words, all I did was a bunch of substitution. Are we good so far? I just substituted a whole bunch of unknown or variables with actual values in the example. So when we look at this, we go like, okay, what is the big deal of 16 minus 1, which is 15, and then 15 minus 3? So the importance of this one has to do with, there are two things. One is, let's work it out in actual base 2. So we are looking at 15 minus 3 in base 10. Okay, so now I want to do it in base 2. Okay, what is the binary representation of 15 as a quantity? Very good. Okay, I like the quickness of your answer. Okay, so it is 1, 1, 1, 1. And what about 3? 0, 0, 1, 1. Very good. So now, you guys go like, oh, tech is going to do that, x, y, um, x, y, q, t, d in this case. And the thing is, I don't think I want to do that. I don't think I need to do that. Why don't I need to do that? Because there won't be any borrow of 1. Okay, so I just claimed something. I said in this particular calculation, I'm guaranteed to have no borrow of 1. All the borrows are going to be zeros. So can someone tell me why that is the case? Yes, all the x are 1s, okay? But then somebody's going to say, but what about q minus t? That can also give us a borrow of 1, okay? So what is the argument against that one? Okay, so think about it. Okay, there are two sources of a borrow of 1. Okay, so you can have a borrow of 1 from the subtraction of x and y, and then you can also have a borrow of 1 with q and t. So we guarantee that the borrow of x minus y is guaranteed a 0 because x is 1. In base 2, okay, can any digit be can any digit be less than be greater than 1? I should say as greater than 1. The answer is no. Okay, so if b of xy is a 1, if and only if x is less than 1, and x is already as large as it possibly can be, that means there's no chance b of xy can be a 1. Okay, all right. Okay, fine. What about b of qt then? Because q can be a 0 or 1, okay? Because if x is 1 and y is a 0, q is a 1. If x and y are the same, then q is going to be a 0, and then it depends on t. Well, I'm just going to say that I know that all the t's are going to be zeros. Then you guys go like, but you can only guarantee that for t of 0, the least significant t. How can you possibly make sure the other t's are also zeros? Well, because this whole equation here computes t of I plus 1. Okay, so if I were to introduce the bit position, t of I plus 1 equals to b of xi yi or b of qi ti. I won't introduce the entire proof here because it is called proof by induction. So in proof by induction, if I know there's a base case where t of 0 is a 0, and I can use an induction step to show that, hey, if t of k is a 0, then t of k plus 1 is also going to be a 0, that completes the whole proof, okay? If you have not taken CISP 440, try to jot down some notes, okay, and go like, okay, when I take CISP 440, I might want to revisit this particular proof. If you have taken CISP 440 already, you might want to work this out, when you have time, okay, not right now, but when you have time, because proof by induction is one of the most useful techniques in mathematical proofs in computer science. The other one is proof by contradiction. Okay, so you guys may say, but Tech, why don't you just focus on teaching CISP 310 and leave 440 to whoever is teaching 440? Well, I got two answers for you because I also teach 440. Yes. Nope. That is proof. That is so proof by contradiction is not. I have to remember the term. it's not the same thing as a counterexample. Okay, so what you were referring to is called a counterexample. To prove a theorem is not true or is not sound, you only need one single counterexample. But to prove that something is in fact true, you can use proof by contradiction, which negates the premise in the first place, and then you have to arrive to a contradiction with everything else that you're given with. So there are two different things. One is to prove the theorem is wrong, and the other one is to prove the theorem is right. Okay, very good. But getting back to the explanation of why I talk about proof by contradiction and also proof by induction is, do you think all your classes are contained with its own little container, and you don't need, once you have taken this class and you're taking the next class, you don't need anything from the previous class anymore? Hmm? Depends on the class, yes. But I would argue that all classes are related, especially if they're in the same discipline, they are all related. And it also means that if you're taking a class, okay, let's say you're taking three classes, okay? Let's say you're taking CISP 310, this class, 440 and 430 in the same semester, okay? That's a pretty heavy load, okay? But if you can relate the topics between the classes, you might feel that you're only taking maybe a one and a half or at the most two classes, because those three classes are related in strange ways. Okay, 310 and 440 can be related because we talk about base conversion, we talk about logic. Okay, so those two classes have certain things that are common, at least related. 430 and 440 are certainly related. Okay, the whole concept of recursion, and recursion relates to this class too, just later on. Okay, so if you see all the common threads between the classes. Oh, this class talk about this concept, but it actually is also related to this in this class. One, you won't feel your load to be as heavy, and two, you get a more in-depth understanding of the material because the material, the concepts are no longer disjoint and standing on its own. Now you see all the bridges between the concepts as well, which also means later on, because remember, getting your bachelor's degree is not the end game. Okay, except for some people who have retired or rich enough and go like, yeah, I'm just getting my bachelor's degree for fun, okay, because I have enough money already. I don't need to get a job. But I think most of you are thinking, I want to get a job in computer science. So that means passing a class is not your end game. Okay, your end game is to enter, is to get a career going in computer science or a related field like data science or modeling, data modeling, and so on and so forth. So if finishing your degree is not your end game, then you have to think longer term, which is how do I build as much knowledge as possible and figure out the relationship between all the pieces that I've learned, because that is how you can more efficiently apply what you have learned to solve problems. It is not about how much you know, it is about how quickly you can solve problems when you're in a career. Okay, so that's, I know it sounds like nagging, but I used to be a hiring manager in industry, so I kind of, the way I look at whether I'm successful in a class is how many people in this class at the end of a semester would prove themselves to be people that I would hire if I were the hiring manager. That's how I look at student success. It is not your grade, it is not your GPA, it is, well, do I think this person is someone I want to hire to get the job done? What job? It can be anything. Okay, by the time you go out to get a job, there will be job titles that do not exist today, guaranteed. Right? Because just because progress, is so quick these days, there's no way I can predict what kind of job, or job titles you guys will be dealing with. Okay. So I know that's a digression, but I believe it is important as a digression, okay? Because I don't want people to think, oh, I just need to get past this class and then I'll be good, okay? Nope, nope. All the classes are related, okay? So you need to retain all the knowledge, all the things you have learned also. Okay, so anyway, the bottom line here is I can guarantee that the entire row of t are zeros. Okay, so now we actually perform the subtraction, and you go like, ah, okay, that looks like an interesting pattern, don't you think? Because this is x, this is y, and this is d, okay, for difference. And in this case, y is actually the same thing as tilde d. You guys goes like, what do we mean by tilde? Okay, this tilde symbol, which is on your keyboard, shift back tick, okay, is bitwise not. That is what it means. Okay, it is called bitwise not. So bitwise not simply is saying, hey, if this is a 1 here, turn that into a 0, its own negation. If this is a 1, turn that into a 0, which is its own negation. This is a 0, turn it into a 1, which is a negation. This is a 0, turn it into a 1, which is also negation. And I'm talking about logical negation and not arithmetic negation. Are we seeing the pattern? Are we understanding that when you subtract a binary bit pattern from 2 to the power of w minus 1, the whole thing becomes just it just becomes bitwise not. Every bit position turns into its opposite. We're not talking about x, we're talking about y, the relationship between y and d. Are we seeing that? Okay? So that is important because so I am answering a lot of questions that I think people really should ask, which is, the why, the how, and what. Okay, not necessarily in that order, but those are important questions to ask. So in this case, okay, so I'm not finishing up the proof by induction here. So D is the negation of Y, or Y is the bitwise not of D. They are equivalent. Okay. In other words, you can put a tilde on one side, on this side, on the right hand side, or you can move the tilde on the left hand side. It's still fine. Yep. Bitwise not. Yeah, you can look at it that way too. But more importantly, it is also just bitwise not. Okay. So bitwise not has a special name. Bitwise not is also called one's complement. So in this class, I use C1 to denote one's complement. So when you hear the word one's complement in this class, all that means is bitwise not. For every bit position, if it was a 1, it turns into a 0. If it was a 0, it turns into a 1. So are we okay so far with what is one's complement? Okay. So if it is one's complement, that means this whole thing, the negation, the arithmetic negation of v, is no more than just the bitwise not of v as a bit pattern plus 1, because this whole thing turns into bitwise not of the bit pattern. Are we making that association? Let me use the mouse pointer here. I'm talking about this entire parenthesized expression just becomes bitwise not of v. Are we good so far? Okay, so I'm seeing a few knots here. Okay, that's good. So by definition, this whole thing, the bitwise not plus 1, is called two's complement. So the two's complement of a bit pattern x is defined as the one's complement of the same bit pattern x plus 1. And I claim that this is doing the same thing, the very same thing as arithmetic negation of v as a bit pattern. All right, so I see a few confirmation that this is okay. So what we'll do is now we're gonna take a look at a few examples and see whether that works or not. Okay, so tell me one property of arithmetic negation. There are two important properties of arithmetic negation that we should be able to prove. Okay, if I claim that two's complement is the same thing as performing an arithmetic negation, I should be able to perform those two tests and go like, oh, okay, I see how it works the same way as arithmetic negation. So what are those two? The arithmetic negation of the arithmetic negation of some value is the original value. So we'll go ahead and give it a try. Okay, so that's what we're gonna do. So I'm saying that the negation of some value x is just x. Okay, that's in algebra. Okay, so in your math professors will be able to tell you this. But now, if I say that the two's complement is doing exactly the same thing, then I'm basically claiming that this two's complement of the two's complement of x should also be just x. Okay, but I can show you a few examples of how this works. So someone can give me a value to test. Okay, you can give me positive values from 0 to 7 or negative values from -1 to -8 because those are the values that I can have on a on the wheel that we have been dealing with. Okay, go ahead. Hmm? 7? Okay, we'll use 7. Okay, so we'll try that out. So now we're going to work with the two's complement of the two's complement of 7. But remember, two's complement only works with a binary representation. Can someone tell me what is the 4-bit representation of 7? That is correct. Very good. All right, so now we expand this. Okay, we leave the one on the outside alone and then expand the inside one. It is the ones complement of the same bit pattern plus 1. So that becomes, um, flipping all the zeros into ones and all the ones into zeros. It becomes 1, 0, 0, 0 in base 2 plus 1. Then it becomes the two's complement of 1, 0, 0, 1 in base 2. And now this becomes the one's complement of 1, 0, 0, 1 in base 2, the whole thing plus 1, which then becomes, the basically it's the bitwise knot of 1, 0, 0, 1. So that is 0, 1, 1, 0 in base 2 plus 1, which is 0, 1, 1, 1 in base 2. Are we good so far? Okay. So all I did was to reapply what we have just learned, the definition of the two's complement. So the explanation of today's lecture or the content of today's lecture, there are two distinct parts. One is how does two's complement work? And the second part is, our examples. So there's a theoretical side using um, congruent modulo math, okay, to kind of to explain why we can express negative values using only a bit pattern. And then the second part is to explain why two's complement should work from the mathematical perspective. This is just an example. Are we good so far? Any questions? Okay. So what is the other thing about negation that you think, I think it should work out in this case too? What is the arithmetic negation of 0? Yeah, go ahead. Why do we start with two's complement? Oh, you mean why we are expanding this one first and not expanding the outside C2? I'm not sure what you mean by that. Okay, are you asking why we expand this part into this part? You mean from this expression to this expression? This is by definition, C1 of something is a bitwise knot of the bit pattern, and that's why we ended up with 1000 in base 2. That is its definition. I'm just carrying out the actual operation. Yes, exactly. Yep. All right. All right, so the second thing we're going to do is to say, what about the negation of 0? So in mathematics, what is the result of the negation of 0? It's just 0. Okay, very good. So, okay, wrong pen. There we go. Well, we'll see. Right? We're actually gonna do this. Was that your question? Whether the two's complement of 0 is just going to be the highest value? I think that was what you said, but I could have misheard. Okay, so we'll work that out. Okay, so we look at the two's complement of 0, 0, 0, 0 in base 2. It becomes the one's complement of 0, 0, 0 in base 2, the whole thing plus 1, which is 1, 1, 1, 1 in base 2 plus 1, which is 0, 0, 0, 0 in base 2, because it is fixed with addition. So if you start with 4 bits, your end result should only end with 4 bits. So the extra bit, which is the bit 4, is not counted as part of the sum in this case. Yep. Well, it is not lost per se. It is remembered as the carry flag, as the overall carry. So whether the carry flag has any useful meaning depends on the context. In this case, it does not. Yes. Yeah, because of congruent modulo math. Remember, when you move a whole circle, you go back to it yourself. So if you are already at 1, 1, 1, 1, okay, so I'm gonna be careful and just use my pen, okay, instead of my hand, because this time it may be misunderstood, okay. So on the wheel, you're already pointing here, and you're just gonna move one more click, tick, like this, right? That is 0. Okay, 12 o'clock is 0. And you're already close to 0. You're just one click away, and now it becomes 0 and not 16. Because 16 cannot be represented, on that wheel. So is that okay? Does everybody understand why 1, 1, 1, 1 plus 1 is 0, 0, 0, 0? Okay. Because otherwise we'll need 5 bits to represent it, and we only have 4 bits. Okay. Any other questions? Well, I think this is kind of magical, okay? Okay, not magical, but it's kind of cool, okay? It's kind of cool that we can use logic gates to perform two's complement, okay, to perform arithmetic negation. So arithmetic negation is helpful in many cases because I can now ask you something like, what is the um, arithmetic negation of 001101, okay, as a 6-bit pattern. So you go like, okay, this is the value of 13. So I just need to represent negative 13 in 6 bits. How do we do it? Well, this whole thing is the same thing as C2 of 001101 in base 2, which I'm going to shortcut this as 1100 10 in base 2 plus 1, which is 110011 in base 2. In other words, without drawing a rather large number wheel, because this one's going to have 64 slots, okay, I can just go through this computation and quickly find out, what is the representation of negative 13. Yep. Because I want to prove to you guys, or not so much proof, but to illustrate, the properties of arithmetic negation is preserved by two's complement, because two's complement is the actual mechanism to perform arithmetic negation when all you have are logic gates. Okay, so are we good so far? All right. So now we're going to move on to, if you're given a certain bit pattern, what is the value that it is representing? Okay, so in the signed representation. Okay, so I'm going to give you some random bit pattern here. Okay, as this is the bit pattern. Okay, and I say that okay, I look at this. I want to look at this as a signed. I want to interpret this as a signed value. Okay, so that's a given. Okay, I give you the bit pattern. I tell you ahead of time, I want to look at these 6 bits as a signed, I want to interpret it as a signed value. Okay, so the question is, can we quickly figure that out? Okay, well, one thing you can do is, draw that, 64 slot, number wheel, and then just do your counting. Okay, just match up the bit pattern with the value that it is supposed to be representing. That certainly will work. And I would like to see someone try when we work with 64-bit numbers, because that wheel is going to have 2 to the power of 64 slots. That is a lot. Okay. Okay. Let me just cut it in half. 32 bits. Okay. If I'm dealing with 32 bits, how many slots are on that wheel? Yep. Yep. And how long do you think it's going to take you to to even to put all the slots in? And a gigantic piece of paper too. Hmm. Yep. So it's nice to be able to look at the bit pattern and quickly figure out, how it is computed. So I will show you the math here. Okay. For the most part, it is just like base conversion with one minor little tweak, which is actually super important. So I have one of one, I have none of two, I have one of four, none of eight, I have one of 16. And then now when we get to the 32, we go like, let's subtract the 32. Okay. So we'll work out this math here, and then we'll work out using two's complement and see if they match or not. So in this case, we have what, 21 minus 32 in base 10, and that is negative 11. Okay. So I claim that if W is 6, the bit pattern of 110, 101 in base 2 is representing, if it is interpreted signed, then it is representing the value of negative 11. That's what I'm claiming. Okay. So now you guys are go like, okay, how do we double check? Tell me how we're going to double check. Exactly. Okay. So we're going to do the C2. Okay. So we say that negative, mm, okay. Let's just do the C2. Okay, we'll do the C2 of 110, 101 in base 2 is, I'm shortcutting the whole thing. It is because it's, we just flip the bits, from 0 to 1 and 1 to 0. So it's 1 is 0 0 1 0 1 0 plus 1, which is then 0 0 1 0 1 0. Oops, take that back. 1. There we go. And that one we can kind of quickly convert, right? There's 1, there's a 2, there's an 8. 1 plus 2 plus 8 is, in fact, 11. Okay, so we go like, okay. So if the two's complement of a particular bit pattern is 11, what do you think that particular bit pattern is representing? Remember, two's complement is the same thing as arithmetic negation. So if the arithmetic negation of 110, 101 is 11, that means the pattern itself is negative 11, because the negation of 11 is 11. Are we doing okay? Yep, that is correct. So in terms of the notes, and I am shocked that nobody read the notes. That is not going to work in a 4-year university, but I'll leave people to find that out later. Okay. So I have two definitions here. VU is saying the value of a bit pattern of X interpreted up to W bits that is unsigned. So it is the unsigned value of X as a bit pattern up to W bits. And what do you think VS is? The signed, exactly. So the VSXW says this is the signed value of the bit pattern X interpreted up to W bits. Is that okay? Does everybody understand what the notations are trying to say? Okay. So one is pretty straight up. Okay. When you look at this definition here, you go like, isn't that really just a special case of the base conversion thing? The answer is yes, absolutely. It's just straight up base conversion, okay? Because we know the least significant bit is position 0 and the most significant bit is position W minus 1. So we just know exactly where to start and also where to end. And because the base is 2, that's why we are only dealing with powers of 2. So now you look at VS and go like, isn't that about the same thing? Well, the answer is yes, it is about the same thing because the sigma notation is almost exactly the same with one tiny little difference. This one only goes from 0 to W minus 2. In other words, the most significant bit is like, that's not part of the sigma. Where does it go? It goes right here. This is the most significant bit. The most significant bit, which can be a 0 or 1, is multiplied, yeah, multiplied to 2 to the power of W minus 1, but it is subtracted from the original sigma. So that's the only difference. Signed versus unsigned interpretation as a bit pattern. How do you figure out the value? These two equations. The first one, VU, is for unsigned, VS is for signed. Are we doing okay so far? All right. So now I just have a few examples down here, okay, or as a quick exercise, we'll do it together, okay. So with VU, okay, unsigned interpretation, we have 0 plus 0 plus 4 plus 8, so this is just 12. With the signed interpretation, we have 0 plus 0 plus 4 minus 8. So this is negative 4. Is that okay? All right. And that's it. That's the end of the signed versus unsigned module. Okay, cool. And there are some exercises too, okay? They're generated by AI, okay? And the prompt is actually here as well. So for those of you who want some additional practice, questions, you can certainly copy this prompt, to your own ChatGPT conversation, modify it however you want, and generate your own, test questions. Because one fairly common complaint that I get from my students is, I don't provide enough chances for practice. Okay, but with ChatGPT, it's actually pretty easy. How many people have started to use this strategy with your other classes? You're using ChatGPT or some LLM to help generate more examples to practice on. Okay, very good. And there are some occasions that the AI can be wrong. Okay, so when you have any doubt, it's like, well, I think the answer is this, but the AI tells me the answer is that. You can always bring that example to me, so I can tell you, which way it is. Okay. Are there any questions? All right. And which part of the module or the lecture do you think is the important part? Okay, so I need to qualify that a little bit. So we'll say important in the short run and then important in the long run because the answers can be different. So we'll answer the first one first. Okay, which part is important in the short run? Go ahead. Flipped plus one. Yep. Okay, and the equation of Vs and Vu. So those two are basically the takeaway of pretty much the entire module here. So you goes like, but Tech, you could have done that in 2 sentences. Yes, I could have. So what about the other question? In the longer run, which part is important? In the longer run, it is the reasoning that is important. What is the foundational math that makes this possible, and how does the mechanism work? What is two? Why does two's complement work? Because it is weird, right? Because you take a bit pattern, you flip all the bits, zeros into ones and ones into zeros, and then you have to add one. Why do we need to add one? But now you know why we need to add one, because the whole math derivation is included in the module. Yes. Which symbol are we talking about? No, shebang is not double exclamation point. Shebang is um, pound exclamation point. Okay, because I was just about to do a Google search to confirm my suspicion, because sometimes I forget about stuff too. Okay, but that's unrelated to what we talk about here, because shebang is how you use a bash script or how you write a file so it knows what program to use to run the rest of the file. Yeah, no, no, because exclamation point is a logical knot, tilde is a bitwise knot. You can consider them to be related, but otherwise, that's where your statement can end. Okay. Okay. So let me explain that, because it is really kind of important too. Because every little bit of thing that may be confusing is actually important. So I'm starting to record it on this side too. Let's stop that. Okay. I click a button somewhere, and oh, I can only click it on this end. Okay. So the question is, if you look at this operator versus this operator, how are they related and how are they different? Okay, so that's a question. So I'm going to ask this question here. So let's say in C++ you have int x here. Okay, and also let's just say that x is 11. I like 11 today. So let's just say x is in 11. So now the question is, if you use the expression tilde x, what is the result of tilde x? No, it is not negative 11 either. All right. Okay, what did we just talk about? The tilde symbol is one's complement. And what does one's complement do? Go ahead. Yep, exactly. Okay, so I don't even know, the number of bits with an int, because it depends on the compiler. Okay, if you are running the compiler on a 32-bit platform, then it is likely that int is only 32-bit wide. If you run the compiler on a 64-bit platform, it is likely that the integer is 64-bit wide. But there are exceptions to that rule. If you're running a C compiler using Arduino, okay, as a IDE, and int is 16-bit. Okay, so I don't know exactly how wide it is, but I know one thing. I know the least significant bit of x. Okay, so we look at x here. So I know the least significant bit of x is going to be, well, we saw that earlier. It is 1011 in base 2, followed by a bunch of zeros. Okay, tilde x is bitwise not. All the zeros turn into ones, all the ones turn into zeros. So that means the 1011 becomes 1 0 1 0 0 in base 2, and all the zeros turn into ones. It is not zero. It is far from zero. On the other hand, when you look at the negation of x, okay, the negation of x, a logical negation of x, is just plain zero, because it's logical. Because in C and C++, in a Boolean context, an integer anything other than zero is true, anything that is exactly 0 is false. So if x has a non-zero value, which is 11 in this case, then the logical knot of x, the logical knot of 11 is 0 because 0 is the only representation of false. Yes. Oh, that's a very good question. I like that question. So the question is, what is not x? The answer of not x is not x. It is not 1. It is anything but 0. That's all you can guarantee. Okay? So this is anything but 0. 0 is the only value that you cannot have with double exclamation point x, because any non-zero value is a true. So if x is true to begin with, not x is false, not false is true again. But do we have a single representation of true in C as an integer? The answer is no. Now, this is where C++ and C differ, because C++ actually has a Boolean type, but C does not. C does not have a Boolean type, which means the only way you can represent a Boolean is an integer. So did your CISP 360 professor get into this kind of detail? No. I did not think so, but these are very important points to remember, okay? Because you do not want to always compare the result of an arithmetic of a logical operation to one as true and compared to zero. Comparing to zero as false is fine, but comparing to one as to confirm it's true is not a good idea. Now, does that mean most compilers do not use one to represent true in a context like this? No, most compilers do use one as the representation of true in the context of an integer. That is true. But is it guaranteed to do it? Is it required to do it? Does the C standard actually say that it has to use one to represent true? The answer is no. So that means don't use it. Do not make assumptions like that. Hmm? Yep. The standard only says true is not 0. Yep. So if x is 0, then not x, logical not of x can be anything but 0. The compiler has no obligation to use 1 to represent not false. Yep. No, I don't think C has that particular concept. Yep. But Java, for those of you who are from Sac State and you took Java as the class, to get into this class here, Java is entirely different. Okay. In Java, if you give it an expression like this, it will come back and say compile time error because the types do not match. 0 is an integer, and you cannot perform a Boolean operation on an integer in Java. So in Java, you just cannot say something like this because it simply is it's a compile time error. But in C, you can do it. Okay. In fact, that's the only way to do it in C. C++ is kind of somewhere in between. If you say the logical not of an integer value, it will coerce the result back into a Boolean. Is that okay? All right. All right. So we're going to take a quick preview of the next topic. We have enough material for today's lab. So we are going to take a look at the next topic because you're going to have like what 5 days before we meet again. So I have to plan for you how to use the 2 extra hours for each hour of lecture. Yes, go ahead. According to the syllabus, it is, yep, about 1/3 through the semester. We are not close to 1/3 yet. Week 5-ish, 6-ish, yeah. All right, so the next topic is not an easy one either. So I also recommend people to read ahead of time. This one is about binary comparison. In other words, I have a value x, I have a value y. How can I tell that x is less than y? And yes, you heard me right. I'm only interested in less than. Then what about greater than? What about equal to, greater than or equal to, less than or equal to, and not equal to? Yep, yep, because all of the other ones can be derived. And I think there is a little bit of, oh, this is an interesting module. I like this module because I put green boxes around all the actual important things. Okay, let me let me retract that statement. The green boxes are the things that are important in the short run, but the whole module is important in the long run. Okay, so that can help you prioritize how you use your time. Okay, and how you you know, you need, if you need to, you might need to do a trade-off between short-term stuff versus long-term stuff. But I hope you guys all have the time and the resources for the long-term stuff. Okay, so the reasoning and the explanation is all throughout, but the green boxes are kind of the bottom line of everything. All right, so I will still need to give you the access code to the lab. Okay, and just to re-emphasize, people are expected to do the lab, in the actual lab. This is an in-person class with an in-person lab, so the lab portion is not supposed to be done, at home, which one person did and then quickly dropped the class because I refused to help this person when he said, "Well, I'm actually home. Can you Zoom so that you can help me with the lab?" I go like, "Nope." So that person dropped the class. Anyway, you need to know the lab thing, which is two's complement. Okay, not surprising. Okay, the name, and this is the access key. It is negative. All right, I'll see you in about 12 minutes.